Here we are at chapter 24, but before diving into that, let's look at power delivered to our homes by the power company. Here is a diagram showing a typical home voltage system from the power company. A transformer in the neighborhood reduces the voltage to 240 volts between this leg and this leg. A center tap on the transformer provides half that voltage between each leg, 120. Devices that draw higher currents will use that 240 for operation, but most of the circuits will develop that use the 120. Here's our main panel where the main circuit breaker is, and we have a lot of different circuits here, but the 120 volts here will have cables rated for the current that's connected to that circuit breaker. And then we'll have the higher current users using 240 volts, and again the current will be rated, the cable will be sized according to the amount of current that it will draw according to the circuit breaker. Here's an example of high voltage coming to the neighborhood. Then this would be in the neighborhood. This might be a substation voltage, and then this will be delivered to the home. So chapter 24, we're talking about three-phase systems, and read these sections 1 through 15. This is a generator. Now, these are huge devices if you've ever visited a power plant. One complete shaft rotation, 360 degrees, of an AC generator provides a single sinusoidal waveform. And we're going to concentrate on three-phase systems. The electrical generator here, broken down to the main pieces, has some basic parts. It has a stator and a rotor. The rotor is the moving part, and it represents the magnetic field source. And this is a very simplified idea here in what we're showing. And then we have the stator, which develops the EMF voltages at the end of their cables. EMF is electromotive force. And that'll give us the three-phase voltages that we use in our three-phase systems. So this is just a high-level understanding of a generator. We're not developing generators in this course. The rotor, which isn't shown here, would go by, this is the stator coils, would go by the stator, each coil, and induce a voltage and develop a sinusoidal voltage. Each coil here is identical, and they're 120 degrees apart. For a 60 hertz system that's used in the US, the rotor in a 60 hertz generator will cover the full 360 degree rotation in 16.67 milliseconds, and that's 1 over 60. Here is the result of our generator, of the AC generation. We have three phases generated 120 degrees apart. Three-phase system delivers power to the grid. It's very efficient. We can use lighter weight cables, and the support for that will be lower cost. If we have the three-phase system, it provides smooth operation to allow a large motor to start easily. Because when one of the signals is at 0, the other two are 87% of their positive or negative maximums. And I also want to give some recognitions to people that helped us develop these three-phase systems used today. The stator coil generates the voltage of each phase. They're 120 degrees apart, as we mentioned earlier, provides a smooth delivery of power. And notice that the red signal starts 120 degrees apart from when the origin of this green started. And also the purple or blue started 120 degrees after the red, or 240 degrees after the green. The respective voltage expressions written up here above for the three-phase voltage is the peak waveform, EM, is here the same for each of them. Then we have a sine omega t, and we have at the 0, and this one's a minus 20 for phase B. For phase C, it's minus 240. Remember, to the right is minus and to the left is positive in these waveforms shifting. We could say this is minus 240, or we could go on the other side and say it's plus 120. This graphic here shows a three-phase Y, and some people call it a star system, but it's an upside down Y here. And we'll notice that this is the generator with the three coils, stator coils, going into a load. We have a line-to-line voltage, which would be A to B, or A to C, or we have a line to neutral, which we call phase voltage, A to neutral, B to neutral, and C to neutral. And in a Y system, the line to line, notice that it has two coils, a line to line, and that should be greater. So the line voltage is square root of 3 times the phase voltage. The phase voltage is considered the line to neutral. This is a delta system. We have a delta generator and a load here. In a delta system, we notice that the line to line is the same as the line to phase. So a voltage of the line to line equals the voltage of the phase voltage. However, if we look at the currents, and the current of the line and the current of the phase voltages, the line voltages should be greater. So the line voltage equals square root of 3 times the phase. There's no neutral connection, but there can be a center tap with a delta system. There are 4 possible connections between the generator and the load, and I have them listed here, Y to Y, and that's what we're showing here, Y generator and Y load. Or it could be a Y delta, a delta Y, or a delta delta. Let's do some examples here. If we look at this Y connection to Y connection, what is the line voltage, the line to line, A to B, A to C? We're given the phase voltage, the line to neutral, is 120 volts. We're given the load, and they're all balanced, they're the same. So the line voltage equals the square root of 3 times the phase voltage. Let's go to our next slide. So the line voltage equals square root of 3 times the 120 volts, which is the phase voltage. We get 208. All the line voltages have the same magnitude, 208. And I'm pointing them out with the red circles here. For the load having a 3 ohm resistor and a 4 ohm inductor, we want to first find the Z impedance for example 1. And we know how to do that. It's 3 squared plus 4 squared square root of to find Z, and that's 5. And we find this is, since it's an inductor, it's going to be positive. We have we do the arctangent of 4 over 3, and we get 53 degrees. Next, we determine the phase current of the load. The magnitudes of the current on each line are the same. The phase current equals the line current for a Y system, but the phase shift is different, as shown. So we have it all laid out here. We divide 120 divided by 5. We get 24. We have different phase shifting, but the same magnitude. So note that the current on the line is equal to the current going through the 3 ohm and the 4 ohm and the 3 ohm resistor and a 4 ohm inductor. Example 2. We have a Y generator and we have a delta load. We want to determine, and the line voltage is 240, that's been given to us. So the line to line is 240. Determine the phase currents through the loads. First we compute Z, and the load is balanced. We expect the current magnitudes to be the same, but different phase. So we'll go to our next slide here. We now divide the voltage magnitude by the impedance magnitude and subtract the angles. We get 24 amps at the various angles. This is the phase currents at the load. Next, we compute the line current in the delta load. We understand that 24 amps is going to each load. So the line current should be greater. And we compute that by the line current in this system in the delta load is square root of 3 times 24, which is our phase current. And we get 41.5 0.52 amperes. Example 3, we have a delta Y system. And this is an RC, so this time we have a capacitor, RC load. So we know that Z equals 6 minus J8. And we can compute that in polar coordinates, and we get 10 at minus 53. This is negative because it's going, that impedance vector is going negative. We want to compute the phase voltages across the load. We know that the current and the impedance will help us compute the voltages across the load. Because we're using Ohm's law, voltage equals current times resistance. So we compute 20 volts, the phase voltage across each load. So we had the 2 amps times the impedance, and we get 20, and we get these different phase shifting. Next, we find the line voltage supplied to the Y load. The line voltage shown in red. We know that in a phase, we know that the phase voltage in a Y system, VL equals square root of 3 times the phase voltage. So we know the phase voltage. Now we'll just compute the line voltage. Square root of 3 times 20 volts gives us 34.6 volts supplied to the load. That's it. So chapter 24, do these homework problems. Thank you.